Hello my dear student, welcome to EPG Pathsala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hind University. Today we are going to discuss about the module titled Basic Properties of Nanomaterials Part 5th under the paper Nanoscience and Technology Part 2. After completing this module, the student will able to learn the wettability and contact angles. They also know about surface area of nanomaterials, porous material for catalytic activities. So these are the points the student will learn after completing this module. Yes. Wetting force are in plane or around us. They have practical application such as making rain bead upon a freshly waxed car so it is protected from rust, and they provide vismy wetting force, bind sand grains to hold the shape of child sand castle. Forces of wetting influence hydrocarbon reservoir behavior in many ways, including saturation, multi-phase flow, and certain log interpretation parameters. However, before getting into these details, it is best to first establish what wetting and wettability describe the preference of a solid to be in contact with one fluid rather than another. Although the term preference may seem odd when describing an inanimate object, it aptly described the balance of surface and interfacial forces. A drop of preferentially wetting fluid will displace another fluid. At the extreme, it will spread over the entire surface. Conversely, if the non-wetting fluid is dropped onto a surface already covered by the wetting fluid, it will bead up, minimize its contact with the solid. If the condition is neither strongly water wetting nor strongly air wetting, the balance of the forces in the oil-water solid system will result in a contact angle theta between the fluid at the solid surface. In many oil field applications, wettability is treated as a binary switch. The rock is either water wet or oil wet. This extreme simplification marks the complexity of wetting physics in reservoir rock. In a homogeneous porous material saturated with oil and water, strongly water wetting describe one end member of continuum in which the surface strongly prefer contact with water. A strongly oil wetting surface prefer contact with oil. Degrees of wetting applies along the continuum, and if the solid does not have a marked preference for one fluid over the other, its condition is termed intermediate wetting or neutral wetting. Reservoir rocks are complex structure, often comprising a variety of minerals type. Each minerals may have a different wettability, making the wetting character of the composite rock difficult to describe. Typically, the primary constituent of reservoir, quartz, carbonate, or dolomite, are the water wet prior to the oil migration. This brings up further complexity. The saturation history of material may influence surface wetting, such that pore surface that has been previously contacted by oil may be oil wet, but those never contacted by oil may be water wet. Various terms has been used to describe both these conditions, including mixed, fractional, and Dalmatian wetting. In this article, the general term mixed wetting will be used for any material with inhomogeneous wetting. It is important to note the fundamental difference between intermediate wetting, means lacking a strong wetting preference, and a mixed wetting having a variety of preference, possibly include intermediate wetting conditions. Another important distinction is that preferentially water wetting surface can be contact with oil or gas. Wettability does not describe the saturation state. It describes the preference of solid for wetting by a certain fluid, given the presence of that preferred wetting fluid. Thus, a water wet rock can be cleaned, dried, and fully saturated with an alkane, while the surfaces in the pores remains water wet. This can be easily seen. Dropped such an oil saturated but water wet rock into a beaker of water and it was spontaneously imbibed a significant quantity of water by expelled oil. Strictly speaking, the term imbibition refers to an increase in the saturation of the wetting phase, whether this is an spontaneous imbibition process or a forced imbibition process, such as water flood in the water wet material. Conversely, drainage refers to an increase in saturation of non-wetting phase. However, in practice, the term imbibition is used to describe a process with increasing water saturation, and drainage is used to describe a process with increasing oil saturation. Care should be taken when reading the literature to determine which sense is being used. I want to discuss the definition of wettability. Wetting is the ability of a liquid to maintain contact with a solid surface, resulting from intermolecular interaction when the two are brought together. The degree of wetting or wettability is determined by a force balance between adhesive and cohesive forces. Wetting deals with the three phases of materials: gas, liquid, and solid. It is now a center of attention in nanotechnology and nanoscience due to the advent of many nanomaterials in the past 2 decades. For example, graphene, carbon nanotube, boron nitride nanomesh. Wetting is important in the bonding or adherence of two materials. Wetting and the surface forces that control wetting are also responsible for other related effects, including capillary effect. There are two types of wetting. The first one is non-reactive wetting and the second one is active wetting. The contact angle. The contact angle is the angle conventionally measured through the liquid where the liquid vapor interface meet a solid surface. It quantifies the wettability of a solid surface by a liquid via the Young equation. A given system of solid, liquid, and vapor at a given temperature and a pressure has a unique equilibrium contact angle. However, in practice, contact angle hysteresis is observed, ranging from the so-called advancing maximal contact angle to receding minimal contact angle. The equilibrium contact is within those values and can be calculated from them. The equilibrium contact angle reflects the relative strength of the liquid, solid and vapor molecular interaction. The shape of a liquid vapor interface is determined by the Young-Laplace equation, with the contact angle playing the role of boundary condition via Young equation. The theoretical description of contact arises from the consideration of thermodynamic equilibrium between the three phases, the liquid phase, the solid phase and the gas or a vapor phase, which could be a mixture of ambient atmosphere and an equilibrium concentration of liquid vapor. The gaseous phase could be replaced by another immiscible liquid phase. If the solid vapor interfacial energy is denoted by sigma Sg, the solid liquid interfacial energy will be denoted by sigma Sl, and a liquid vapor interfacial energy is denoted by sigma Lg. Then the equilibrium contact angle theta c is determined from these quantities by Young's equation. Sigma Sg minus sigma Sl minus sigma Lg cos theta c is equal to 0. Let us talk water wet reservoir rock. Water and oil or gas in reservoirs coexist in an immiscible state. For example, the water phase does not mix miscibly with the hydrocarbon phase. There is a natural and strong interfacial tension between the two fluids that keep them separate, regardless of how small the individual droplets may be. A common example of this immiscible nature is a household salad dressing made on oil and vinegar. In all reservoirs, connate water is immiscible with oil or gas, but chemical can be injected into the reservoir to reduce the interfacial tension and make the water phase miscible with the oil. There are advantages in doing this, and it is a form of enhanced oil recovery. The oil and the gas phase in the reservoir also generally behave immiscibly. However, at certain pressure, temperature and composition, they may become miscible. Throughout this chapter, the three fluids or phase, oil, gas and water, are considered to be immiscible. On all interface between solid and fluid, between immiscible fluid, there is a surface free energy resulting from natural electric forces. The force causes molecules on the same substance to attract one another through cohesion, and molecules of unlike substance are attract one another through adhesion. Interfacial tension results from these molecule forces causing the surface of a liquid to form a smallest possible area and act like a membrane in tension. Wettability can be defined as the ability of a fluid phase to preferentially wet a solid surface in the presence of second immiscible phase. In the reservoir context, it is referred to the state of rock and fluid system. For example, whether the reservoir is water or oil wet, there are three possible states of wettability in oil reservoir exist. Wettability is generally classified into three categories. The first one, the reservoir is said to be water wet. That is, water preferentially wet the reservoir rock when the contact angle between the rock and the water is less than 90 degrees. The second one is the natural wettability. Case would exist at the contact angle of 90 degrees. And the third is the oil wet occur at a contact angle greater than 90 degrees. Water wet rock. A rock can be wet by water if the contact angle made between the water and rock surface is in between 0 to 90 degree. In this case, the adhesion between the water molecule and the rock molecule is stronger than the oil molecule and the rock molecule. Let us discuss oil wet reservoir rock. Reservoir rock is said to be oil wet if oil preferentially wet the rock surface. This happens only when sigma OS is greater or equal to sigma WS. Or we can say that the adhesion tension must be positive. In this case, the contact angle between the rock surface and the oil molecule lies between 90 degree to is less than theta is less or equal to 180 degree. So it lies between 90 to 180 degree. If the value of contact angle is 180 degree, then the surface is called strongly oil wet. Now let us discuss oil wet rock. This slide shows the wettability of rock surface with oil. Here, the surface contact angle is greater than the 90 degree. Hence, oil will wet the rock surface. In this case, the adhesion between the oil and the rock is stronger than adhesion between the rock surface and the water. Let us discuss interfacial contact angle, various organic liquid in contact with silica and calcites. This slide shows the contact angles for the different organic liquid at different surfaces, silica surface and calcite surface. The considered organic liquid are isooctane plus 7.5 isoclonolide and naphthenic acid, etc. The contact angle for these organic liquids on silica surface are 30 degree, 83 degree, 158 degree and 35 degree. While the contact angle for calcite surface for these organic liquids are 30 degree, 48 degree, 54 degree and 106 degree. Let us discuss the surface area of nanoparticle. Nanoparticles have an appreciable fraction of their atoms at the surface. A number of properties of materials composed of micrometer size grains as well as those composed of nanometer size particles depend strongly on the surface area. For example, the electrical resistivity of a granular material is expected to scale with the total area of the grain boundaries. The chemical activity of the conventional heterogeneous catalyst is proportional to the overall specific surface area per unit volume. So, the high area of nanoparticle provide them with a possibility of functioning as an efficient catalyst. It does not follow, however, that catalyst activity will necessarily scale with the surface area in the nanoparticle range of sizes. Using the unit square meter square per gram for these various geometry, we obtain the expression SR, which is 6 into 10 power 3 by rho d, sphere of a diameter. Similarly, 6 into 10 power 3 rho a cube for a size A, 2 into 10 power 3 rho L for thick disk L, which is less than D, and 4 into 10 power 3 rho D for long cylinder of wire D less than L, where the length parameters A, B, A, D and L are expressed in nanometers, and the density rho has the unit gram per centimeter cube. In the equation 5.3c, the area of the side of a disk is neglected and the equation 5.4d, the area of the two ends of the wire are disregarded. Similar expression can be written for distortion of the cube into a cubic well and quantum wire configuration in figure. Table suggests the density in gram per centimeter cube of third, fifth and second, sixth compound for aluminum, gallium, indium and phosphorus, organic, antimony, zinc, sulfur, selenium, tellurium. The table also given for the specific surface area of gallium arsenide spheroid, long cylinders, wire and thin disc. If we take the size of 4 nanometer, the sphere is 281, surface area wire is 187 and disc is 94. So this way we can calculate that if the size is less, how the disc size and the surface area increases in case of these materials. The specific surface areas for the smallest structure listed in the table corresponding to the quantum dots, quantum wire and quantum well as discussed in other module. The specific surface areas are within the range of typical of a commercial catalyst. The data tabulated above represent minimum specific surface area in the sense that for the particular mass or for the particular volume. A spherical shape has the lowest possible area, and for the particular linear mass density or mass per unit length, a wire of circular cross section has the minimum possible area. It is of interest of examine how the specific surface area depends on the shape. Consider a cube of a side A with the same volume as the sphere of radius r, which is 4 pi r cube by 3 is equal to a cube. We saw that an efficient way to increase the surface area of a material is to decrease its grain size or its particle size. Another way to increase the surface area is to fill the material with voids or empty spaces. Some substances, such as zeolite, crystallize in a structure in which there are regularly spaced cavities where atoms or small molecules can log, or they can move in and out during changes in the environmental condition. A molecular sieve, which is a material suitable for filtering out molecules of particular size, ordinarily has a controlled narrow range of pore diameters. There are also other materials such as silica or aluminas which can be prepared so that they have a porous structure of more or less random type. That is, they serve as a sponge on a microscopic or a micrometer scale. It is quite common for these materials to have pores with diameter of the order of nanometer range. The porous surface area are sometimes determined by Brunner-Evenet-Taylor BET absorption isotherm method, which measures are made on the uptake of gas as a nitrogen by its pore. Most commercial heterogeneous catalysts have a very porous structure with the surface area of several hundred square meter per gram. Ordinarily, a heterogeneous catalyst consists of high surface area material that serves as a catalyst supported or substrate, and the surface lining on its pores contain a dispersed active component, such an acid site or platinum atom, which brings about the accelerate the catalytic reaction. Examples of the substrate of the oxide silica, gamma alumina, titania, in the tetrahedral inatase phase, and zirconia. Mixed oxide are also a common use, such as high surface area silica alumina. A porous material ordinarily have a range of pore size of organosilicate molecule sieve MCM41 which has the mean pore size is around 39 angstrom. The introduction of relatively large trimethylsilane group to replace proton of silanol in the pores accumulates in the porous volume, and the shift distribution of pore to a smaller range of size as shown in the lower left spectrum of the figure. The detection of the nuclear magnetic resonance NMR signal from the 29 silicon isotope of the trimethylsilane group in these molecules sheaves with its plus 12 ppm chemical shift confirms its presence in the pore after trimethylsilation treatment. The active components of heterogeneous catalyst can be a transition ion, and traditionally over the years the most important active component has been platinum dispersed on the surface. Examples of some metal oxide that serves as a catalyst either by themselves or distributed on a supporting material like NiO, Cr2O3, Fe2O3, etc., preparing oxide and other catalytic material for use ordinarily involve calcination, which is the heat treatment at several hundred degrees Celsius. Porous material for catalytic activity. This treatment can change the structure of the bulk and the surface, and this for the catalytically active material beta Bi2MO2O9. We deduce that for calcination in the air, the grain size grow rapidly between 300 to 350 degrees Celsius, reaching 20 minutes, with very little additional change up to 500 degrees Celsius. Sometimes a heat treatment introduces a phase change of catalytic importance, as in the case of hydrous zirconia, which transformed from high surface area amorphous state to a low area tetragonal phase at 450 degrees Celsius. For some reaction, the catalytic activity arises from the presence of acid site on the surface. These sites can correspond to either Brasconted acid, which are proton donors, or Lewis acid, which are electron pair acceptors. Figure sketched the structure of a Lewis acid site on the left and Brasconted acid site on the right, located on the surface of zirconia sulfate catalyst, perhaps containing platinum zirconia SO4. The figure shows a surface sulfate group SO4 bounded to the adjacent zirconium atom in a way that creates the acid site. In mixed oxide catalyst, the surface acidity depends on the mixing ratio. For example, the addition of up to 20% of zirconia to a gamma alumina Al2O3 does not significantly alter the activity of Brasconted acid site, but it has pronounced effect in reducing the strength of Lewis acid site from very strong from pure gamma alumina to a rather moderate value after addition of 20% zirconia. The infrared stretching frequency of CN vibration of absorbed CD3CN is a measure of Lewis acid site strength. The progressive decrease in this frequency will increasing incorporation of zirconia in the gamma Al2O3. So student, let us now summarize what we have learned in this module. We learned that wettability is traditionally of one fluid to separate or adhere to the solid surface in presence of other immiscible fluid. Wetting of the surface depends strongly upon the contact angle theta between the liquid and solid. For a water wet rock between 0 to 90 degree, if theta is close to 0, the rock is considered to be strongly water wet. For an oil wet reservoir, it should be between 90 to 180 If theta is close to 180, the rock is considered to be strongly oil wet. So, we also learned the chemical activity of a particle is strongly dependent on the surface area. Surface area of a material can be increased by generating pores in it. So, these are all we learned in this module. Thank you.